You've probably heard the hype about quantum computers, right? How they're going to solve problems that would take our best supercomputers literally thousands of years. But to get to that incredible future, we first have to solve their single biggest problem, errors. So let's dive into this challenge and the amazing race to fix it.
And this quote from Ted Yoda at IBM Research. Man, it just nails it. The whole game is about building something that's almost perfect, what we call a logical qubit, by stitching together a whole bunch of imperfect parts, the physical qubits. It's a pretty mind-bending engineering challenge.
Okay, so that's the goal. But what's the catch? What makes this so incredibly difficult that it has some of the smartest people on the planet working on it day and night?
Well, it all comes down to the very heart of a quantum computer. It's Achilles' heel. And here's the crazy part. The very thing that gives a quantum computer all its power is also its greatest vulnerability. Think about the bits in your phone. They're super reliable, right? They're like little light switches. They're either on, a 1, or off, a 0. Simple. But a qubit, a qubit is a whole different beast. It can be a 0, a 1, or kind of a ghostly mix of both at the same time. This is called superposition. And while this quantum magic is what makes it so powerful, it's also what makes it unbelievably fragile. The tiniest vibration, a slight change in temperature, anything can knock it off course and destroy the information. We call that decoherence.
So, how in the world do you go about fixing these quantum typos in a system that's so incredibly delicate? Well, the solution actually starts with a concept that's probably more familiar than you think.
You know when you get an email with a typo in it? Most of the time, you can still figure out exactly what the person meant to say. That's because our language has a ton of built-in redundancy. And error correction, whether it's for your computer or a quantum one, works on that exact same principle. You use redundancy to spot mistakes and fix them.
So, a super simple way to see this in action is the classical repetition code. Let's say you want to protect the bit 0. Instead of just sending 1 0, you send 3, 0, 0, 0. Now, if some noise flips one of those bits, and the receiver gets 0, 1, 0, no problem. They just take a majority vote, and can be pretty confident the original message was 0, 0, 0. Easy, right? Well, for quantum, it gets a little trickier.
And here's where things get, well, quantum. See, it's not just about bit flips, where a 0 accidentally becomes a 1. Qubits can also suffer from something called a phase flip. This is a purely quantum kind of error that messes with that delicate superposition state. So any error correction scheme that's going to work has to be able to handle both of these error types.
All right, so for a long time, the reigning champion for solving this two-headed monster of an error problem has been this really elegant idea called the surface code.
So, picture this. The surface code lays out all these physical qubits in a 2D grid, kind of like a checkerboard. But here's the genius part. The information isn't stored in just one of those squares. Instead, it's encoded in the collective properties of the whole grid, in the relationships between all the neighboring qubits.
Now, to really get why this is so clever, we have to do a little mental gymnastics. Imagine taking that flat grid and wrapping it around, connecting the top edge to the bottom, and then connecting the left side to the right. What you end up with is the shape of a donut, or what a mathematician would call a torus.
And this is the magic trick. The actual, logical information, the data you care about, isn't a single point on the donut. It's encoded in loops that wrap all the way around it. So a single, tiny error on one physical qubit, it can't break that entire loop. It's a brilliant use of topology that makes the information incredibly tough and resistant to local noise.
Okay, so the surface code is brilliant, right? Absolutely. But it comes with a massive, and I mean massive, hidden cost. And this brings us to the biggest bottleneck that's been holding us back from building a truly useful quantum computer.
That price is what we call encoding overhead. It's basically the number of messy, imperfect physical qubits you have to wrangle together just to create one single, clean, reliable logical qubit. And for the surface code, that number has been gigantic.
So, what does that look like in practice? Well, get ready for this. To create just 12 useful, protected logical qubits using the surface code, researchers figured you need somewhere around 3,000 physical qubits. Yeah, 3,000 for 12. That kind of overhead has been a huge barrier to scaling these things up.
But what if there was a better way? What if we didn't have to pay that steep a price? Well, some really exciting, recent breakthroughs are showing us that there might just be a more efficient path forward.
Say hello to a new family of codes called Low-Density Parity Check Codes, or LDPC for short. Now, in simple terms, these codes use really clever, sparse connections between qubits to check for errors way more efficiently. And while the surface code is technically a type of LDPC code, these new ones are built from the ground up with that efficiency as their main goal.
And the results? Honestly, they are staggering. To get those same 12 logical qubits that the surface code needed 3,000 for, these new LDPC codes require only 288 physical qubits. Let that sink in for a second. That's a reduction of more than 90%.
Just look at that comparison. This isn't just a small incremental improvement. It is a giant leap. We're talking about an order of magnitude difference in efficiency. This is the kind of breakthrough that could totally rewrite the roadmap for building a full-scale, fault-tolerant quantum computer.
Okay, so this is huge. We've got these super efficient codes. Problem solved, right? Well, not so fast. There's one more really critical piece of this puzzle we need to understand, and that's the concept of the threshold.
So, the error correction threshold. Think of it like a tipping point. If the error rate of your individual physical qubits is below this threshold, then adding more qubits to your code actually helps. It makes your logical qubits stronger and more reliable. But if your error rate is above that threshold, adding more qubits just adds more noise, and the whole system actually gets worse.
And I love how the physicist Scott Aronson puts it. He says the whole point of the threshold theorem is just this. You're correcting errors faster than they're created. That's it. You have to be winning that race against the noise. The threshold is the line where you finally start winning.
So here's the trade-off. The good old surface code, it's a bit more forgiving. It has a threshold of about 1%. These new, super efficient LDPC codes, they're a little bit stricter, requiring a threshold of around 0.7%. But, and this is the key, because their overhead is so much lower, and because today's hardware is already achieving these error rates, they represent a hugely promising path forward.
So where does that leave us? When are we finally going to have one of these fault-tolerant quantum computers? Well, this breakthrough in code efficiency is a massive step. It could accelerate the timeline by years. But the journey isn't over. It's a continuous race between improving our physical hardware to beat that threshold and designing even smarter codes to lower the overhead. The question really isn't if we can build one anymore. It's just how quickly we can put all these brilliant pieces of the puzzle together.